Welcome to this second pre-lecture video for Coordination Chemistry. The aim of this video for week 7 is to reinforce some of the concepts from our discussion on crystal field theory during this first week of the course. The quiz that follows will give you a great chance to test out your skills in predicting some of the electronic and magnetic properties of coordination complexes. You've already seen in lectures, for example, that the magnitude of the crystal field splitting dictates the colour of a coordination complex. It was this question of the origins of colour in materials such as gemstones and even meteorites which contain traces of transition metals that led to the development of the very useful and practical theory called crystal field theory. We've already seen in lectures that each ligand is modelled as a point negative charge. In the absence of a field, all 5 d orbitals are equal in energy. However, if we consider the relative extent of repulsion between the electrons in the lobes of the orbitals for the 5 different d orbitals with the electrons of the 6 point negative charges for our octahedral complex, then we've already seen that they are no longer energetically degenerate. For 3 of the orbitals, the dxy, dxz and dyz, the lobes of the orbitals are pointing between the x, y and z axes. By comparison, the dx squared minus y squared and dz squared orbitals are pointing directly at the ligands. This means that the doubly degenerate set of Eg orbitals, comprised of the dx squared minus y squared and dz squared orbitals, are relatively destabilized in energy, so they're raised in energy, while the triply degenerate T2g set of orbitals, comprised of the dxy, the dxz and the dyz orbitals, are relatively stabilized in energy, so relatively lowered in energy. So in a spherical field, all the 5 d orbitals have the same energy, but in the presence of an octahedral field, we have a crystal field splitting. A single d electron is repelled by the negative charges of the ligands more in the Eg orbitals than in the T2g orbitals, and while it's not obvious, the effect of an electron in a dz squared orbital is the same as that in a dx squared minus y squared orbital. The energy gap between the T2g and the Eg levels is called delta O, O being for an octahedral complex, and you'll equivalently see this written widely as 10 dq, where dq just means differential quanta of energy. We can also work out the relative extent of stabilisation of each of the 5 d orbitals by considering that overall the system must maintain a centre of mass called the barycenter. In order for the centre of mass to be maintained, each of the 3 T2g orbitals must be stabilised or lowered in energy by 4 dq, and each of the 2 Eg orbitals must be relatively destabilised or raised in energy by 6 dq. So let's remind ourselves how to calculate the crystal field stabilisation energy. This is simply the sum of the relative stabilisation energies of the electrons. Here, the d1 electron is stabilised by minus 4 dq. If light of just the right energy is absorbed, the electron can jump the 10 dq energy gap to reach the first excited state. We observe the complementary colour to that absorbed, and in the case of this titanium hex aqua complex, it's a violet coloured aqueous solution. For D2 and higher electron configurations, remember that Hund's rule applies, so 1 electron is added to each of the degenerate orbitals in a subshell before 2 electrons are added to any orbital in the subshell. We can then calculate the crystal field stabilisation energy. In the case of a D2 metal ion, this is minus 8 dq, and for a D3 metal ion, this is minus 12 dq. For the D4 case, the electron could go in one of 2 places, so there are 2 possible arrangements of electrons depending on whether the crystal field splitting, 10 dq, is large or small. If it's large, we call this the strong field case, and the 4th electron will pair with one of those in the T2g orbitals. If the gap is small, we call this the weak field case, and it can easily enter one of the Eg orbitals. We can also see that in the weak field case there are 4 unpaired electrons compared with 2 unpaired electrons in the strong field case. Both the high and low spin D4 configurations are paramagnetic, that is, there are unpaired electrons, and the complex is attracted into a magnetic field. By comparison, a complex with no unpaired electrons is diamagnetic. We can continue building up the D configurations. Here's the D4 case again, and now D5. So the fifth electron can either go into an Eg orbital in the weak field case or the T2G orbital in the strong field case. In the case of the D6 configuration, the sixth electron can either pair into the T2G orbital for the weak field case, and likewise it will pair into the T2G orbitals for the strong field case. In the case of D7, the seventh electron pairs into the T2G orbital for the weak field case and enters an Eg orbital for the strong field case. Now, if we consider a D8 system, we can see that the electron configurations would be exactly the same for both the weak field and strong field cases, and this is also the case for the D9 and D10 configurations. Therefore, there are only 4 D configurations, D4, D5, D6 and D7, which can give rise to both high and low spin complexes. For any D configuration, these are called spin isomers. There are a number of factors that affect the magnitude of 10dQ, and these will dictate the electronic and magnetic properties of metal complexes. In the first instance, you can see from the data shown for these +2 and +3 hex-aqua complexes that 10dQ is larger for the +3 metal ions. The simple explanation for this is that the bonds are shorter and stronger for the 3+ metal ions, such that the extent of electronic repulsion between the electrons in the d orbitals and the ligands is greater. The nature of the metal ion also influences 10dQ. If we consider the cobalt triad, then as we go down the triad, 10dQ increases due to the more diffuse orbitals of the transition metals. We'll talk more about the origins of these trends in 10dQ in lectures. Finally, the nature of the ligand has a significant effect on 10dQ. Ligands such as halides, nitrate, hydroxide and water are classed as weak field ligands and give rise to relatively small crystal field splittings. Ligands such as ammonia, ethylene diamine, phosphine, cyanide and carbonyl are classed as strong field ligands and give rise to large crystal field splittings. While crystal field theory provides us with a simple, qualitative explanation, it does have its limitations, and one of these is explaining the spectrochemical series. To properly understand the placement of the ligands in this series, we need a more comprehensive molecular orbital theory approach, and we'll be discussing this during the next week of lectures. So that concludes our pre-lecture video for this week. The pre-lecture quiz that follows will test your understanding of these concepts. We're looking forward to seeing you in lectures. Good luck.